Hello and welcome to all students. In this lecture, we study about differentiation and we discuss about the gradient of a scalar valued function. So first of all, we define what is mean by gradient of scalar valued function. Then after that we see some examples. After that we see some examples based on gradient of scalar valued function. Then we see some remarks and then algebra of gradient of scalar valued function. Okay, so first of all we see the definition of gradient of scalar valued function. Definition is: let capital S be any non-empty open subset of Rn and let A belongs to S be any point. Let S be any non-empty open subset of Rn and let A belongs to S be any point. Let f from S to R be a scalar field such that partial derivative of f with respect to xi exists for all I is equal to 1, 2, 3, up to n. Then the gradient of function f at point A is denoted by del f of x and is defined as del of f of A is equal to, it is a vector with n components and its first component is nothing but partial derivative of f with respect to x1 at point A, comma, second component is partial derivative of f with respect to x2 at point A, comma, and its nth component is partial derivative of f with respect to xn at point A. Here the symbol del is pronounced as a del. The symbol del is pronounced as a del. So first of all we understood the definition of a gradient of function f. Here S is a non-empty open subset of Rn and A is a point in S and capital F from S to R be a scalar field such that partial derivative of f with respect to all the variables. So all these partial derivatives exist that is dou f by dou xi I from 1 2 3 up to n exist. Then the gradient of function f at point A is denoted by gradient of f of A and is defined as gradient of f of A is equal to, so gradient of f of A is a vector quantity and it is a vector with n components. So first component of that vector is partial derivative of f with respect to x1 at point A. Second component is partial derivative of f with respect to x2 at point A, comma dot dot dot, comma partial derivative of f with respect to xn at point A. Here the symbol del is pronounced as del. Okay, so this is the very simple definition of gradient of function f at point A. So based on this definition, let us we solve some problems. So we have some examples. So write down question number 1. Let f from R3 to R given by a function f of x comma y comma z is equal to 4x cube minus 9x square into y into z plus 3y square z. Find gradient of f at point A where point A is equal to 1 comma 2 comma minus 3. So first we find partial derivatives of the function f with respect to all the variables. So see here in answer, first we find partial derivatives. First of all, we find a partial derivative of function f with respect to variable x, and it is equal to, so we look at the function f and look at the partial derivative of x simultaneously. So partial derivative of f means it is nothing but a derivative of f with respect to x. But while finding derivative of f with respect to x, we have to keep remaining variables means y and z as a constant, and we have to find a derivative. Okay, so derivative of first term with respect to x in f is 12x square. Minus sign as it is. Now we find the derivative of second term with respect to x. So in the second term, y and z, they 9, y and z, they we treat as a constant. So we find the derivative of x square is 2x. So 2 into 9 is 18. So therefore finally we have 18 into x, y, z, and plus in the third term of function f it is 3y square z. So in this term there is no x, therefore all members in the third term are constant, and therefore with respect to x the third term is constant, and if we find the derivative of that third term, the derivative must be 0 because the derivative of constant is 0. Okay, so partial derivative of f with respect to x is equal to 12x square plus 18 into xyz. Now in the similar way we find the derivative means partial derivative of f with respect to the variable y, and it is equal to minus 9x square z plus 6yz. Now partial derivative of f with respect to z is equal to minus 9x square y plus 3y square. Okay, so while finding partial derivative of a given function f with respect to the one variable, then the remaining other variables we have to keep constant and then find the normal derivative. So these are the three partial derivatives that we have to use in the next calculation. So see here, gradient of f of x comma y comma z, it is equal to, so by definition it is, as function is a function from r3 to r, therefore the gradient of function f is nothing but a vector with three components. So first component is dou f by dou x, second component is dou f by dou y, and third component is dou f by dou z. As we have uh, calculated all the partial derivatives, in the second step we have 12x square plus 18xyz, comma, so this plus sign is nothing but comma, we consider here is a comma, and minus 9x square into z plus 6yz, comma, minus 9x square y plus 3y square. So it is a vector with three components. जिथे प्लस साइन झाले तिथे कॉमा कन्सिडर करा. ओके, now gradient of f at point 1 comma 2 comma minus 3 is equal to, so wherever we have a x in the above formula we have to put x equal to 1, wherever we have wherever we have y, so instead of y we have to put 2, and in above formula instead of z we have to put minus 3. So if I put all the values in above formula, then what we get is 12 into 1 square plus 18 into 1 into 2 minus 3, comma, minus 9 into 1 square minus 3 plus 6 into 2 into minus 3. Okay, so in this way we have to put all the values in above calculation, in above formula, then finally we get the gradient of f at point 1 comma 2 comma minus 3 is equal to minus 96 plus minus 9 plus minus 6. So in all we have a calculation minus 101. So gradient of f at point 1 comma 2 comma minus 3 is minus 111. Let us see the example number 2. Okay, question number 2. Let f from r2 to r given by f of x comma y, and it is equal to x into y square whole divided by x square plus y raised to 4 for x comma y not equal to 0 and f of 0 comma 0 equal to 0. Find gradient of f at point 0 comma 0. Okay, we write the solution. We know that gradient of f of x comma y comma z is equal to, so our function is a function from r2 to r, therefore we just have to find a gradient of function f at point x comma y only, means there is only 2 variables, no 3 variables. So gradient of f at point x comma y is nothing but a vector with 2 components, and first component is dou f by dou x, at point x comma y, and second component is dou f by dou y at x comma y. So first of all we separately find out the partial derivatives of function f with respect to x and with respect to y. Also we know the definitions of partial derivatives of x comma y at point a comma b. So these are the definitions of partial derivatives. So dou f by dou x at point a comma b is equal to limit h tends to 0 f of a plus h comma b minus f of a comma b whole divided by h, and dou f by dou y at point a comma b is equal to limit k tends to 0 f of a comma b plus k minus f of a comma b whole divided by k. Hence here f of x comma y is equal to xy square whole divided by x square plus y raised to power 4, and it is not equal to uh, here f of x comma y is equal to xy square whole divided by x square plus y raised to 4, and it is defined for all x comma y is not equal to 0. We put all these in above formula. So first of all we find partial derivative of f with respect to x at point 0 comma 0. It is equal to limit h tends to 0 f of 0 plus h comma 0 minus f of 0 comma 0. So it is equal to f of h comma 0 minus 0 divided by h, and it is equal to limit h tends to 0, numerator is 0 minus 0 divided by h, equal to limit 0 h tends to 0. So limit of 0 is 0 as h tends to 0. Consider the second partial derivative dou f by dou y at point 0 comma 0. It is equal to limit k tends to 0 f of 0 comma 0 plus k minus f of 0 comma 0 whole divided by k. Now dou f by dou y at point 0 comma 0 is equal to limit k tends to 0 f of 0 comma 0 plus k minus f of 0 comma 0 whole divided by k. So it is equal to, in the next step, limit k tends to 0 f of 0 comma k minus 0 divided by k, but f of 0 comma k it is also 0 minus 0 divided by k. 0 minus 0 is 0, so limit of 0 k tends to 0, so limit is equal to 0. Okay, therefore the value Therefore, the value of the partial derivative of f with respect to y at point 0 comma 0 is 0. Now thus dou f by dou x at 0 0 is 0 and dou f by dou y at 0 0 is again a 0. So therefore our gradient of our gradient of function f at point 0 comma 0 is a vector 0 comma 0. Okay, so in this way we have solved the problems based on the gradient of function f. Okay, now we have some remarks. The two space gradient vector in R2 is written as, so in R2 two space gradient vector कसा लिहायचा ते इथे दिलेलं आहे. The two space gradient vector in R2 is written as gradient of f of x comma y is equal to, it is nothing but a vector with two components. First component is dou f by dou x and second component is dou f by dou y. At point x comma y. Now the three space gradient vector in R3 is written as gradient of f of x comma y comma z is equal to dou f by dou x at point xyz comma dou f by dou y at point xyz comma dou f by dou y, sorry, last case is must be dou f by dou z at point xyz. The gradient of a scalar function is a vector. So that is the very important note about the gradient of a vector, and that note is the gradient of a scalar valued function is always a vector quantity. The gradient of a scalar valued function is always a vector quantity. Now we see the algebra of gradient. Let capital S be a non-empty open subset of Rn and let A belongs to S, and suppose gradient of f at point grade G let A belongs to S, and suppose gradient of f and gradient of G both exist at point A, then first identity says that gradient of f plus G exists at point A and gradient of f plus G at point A is equal to gradient of f at A plus gradient of G at A. Now the second identity says that gradient of f minus G exists at point A and gradient of f minus G at point A is equal to gradient of f at point A minus gradient of G at point A. Now next is gradient of, third is gradient of alpha times f exists. Third identity says that the gradient of alpha times f exists at point A and gradient of alpha f at point A is equal to alpha times gradient of f of A. So gradient of, now fourth identity says that gradient of f into G exists at point A, and gradient of f into g at point A is equal to f at A into gradient of g at A plus g at A into gradient of f at A. Now fifth identity says that gradient of division f by g exists at point A, and gradient of f by g is equal to g of A into gradient of f of A minus f of A into gradient of g of A whole divided by g of A is square, provided that g of A is not equal to 0 in a neighborhood of A. So these are the statements of algebra of gradient of scalar valued functions. So in this lecture we stop here, and in the next lecture we will see the proofs of algebra of gradient of the scalar valued function. So let us stop our lecture here. Thank you very much.